that is if they are all
Zero.
zero scalars, okay? That's the only linear combination that we could find to give us the zero vector, okay? Then we had another theorem that kind of said that's true if and only if one of the vectors can be written as a linear combination of the others, okay? In other words, if one of those vectors depends on the other vectors, okay? So in that sense, they're linearly dependent if one of the vectors can be written as a linear combination of the others. They're linearly independent if no vector can be written as a linear combination of the others. And that's important. It says that they're linearly independent. That means there's no redundancy, okay? We need all of them because we couldn't build something if they were dependent, then we wouldn't need one of those vectors because we could build it already from the other vectors, okay? So what we're looking for in a basis for a vector space, and I cannot help but think of my husband's toolbox when I describe this. A basis for a vector space is just the minimal Tinker Toy set, okay? It's the set of vectors that you need to build everything that you want in the vector space through linear combinations, but you don't have anything extra. So we want it to both span, I mean we can build everything, and not have any redundancy. We want them to be linearly independent, okay?
So the bare minimum.
Basis for a vector space is a set of vectors V1, V2 through Vn that is one, spans, I shouldn't say one, that spans the vector space. We can build anything we want from these vectors through linear combinations. And there's no redundancy. The set V1 through Vn are linearly independent. Okay? And I feel like my husband has way too many screwdrivers and all those things because, I mean, he must have.
You can never have too many.
That's
You're
right.
always getting more.
But you can't have too many vectors, all right? So, Tim.
And now with dependent linear combinations, you always let the C value represent some multiple of R, right?
When you're trying to find the linear combination,
When you put it in the final.
that would be if there are many ways to express as a linear combination, okay? We're actually going to show that when you have a basis for a vector space, there in fact is only going to be one, the linear combination will be unique, okay? You can't do it in more than one way. So that's a theorem. But for our examples, like our linear equations, when we were solving a system of equations, we found many solutions, right? So it's sometimes we have many ways to express one vector in terms of the others. Other times we only have one way.
So it doesn't always have to be R then?
No, it could be R or it might be in fact unique, okay? Just like sometimes we have many solutions to a system, sometimes we have a unique solution.
And these are all, this is basically Rn, not just R2 and R3?
Rn, or really the set of polynomials, the set of matrices, any type of vector space, okay? And we'll address that when we get to it. Okay, our first examples will definitely focus on Rn with maybe our typical examples because we don't like things to get too big. So, R2, R3, R4 maybe is as big as we go, but there's nothing different about the method, all right? So, now, we got some theorems to work on. And the first one is our theorem. Here, because I want to make sure that we want to out a few minutes early, James, because I didn't, I want to talk to you after class then. Do you have a class after this?
No.
Yeah, I'm going to talk to you about